Hello, everyone. This video is going to be on section 12.2, and we are going to introduce the concept of vectors. So in the last section, in 12.1, we talked about points in R3. Now we're going to introduce this object called a vector, which I'm conflicted about how to explain it to you because how I think about it is not how the book describes it. Not that the book is wrong, but the book kind of gives you a physics or engineering point of view, and that's not the viewpoint I have as a mathematics graduate student. But we'll stick with the book because that's kind of how your homework's going to be presented, and I suppose how I'll design the tests and all that. And maybe I'll give you some disclaimers along the way. Okay. So how does the book describe a vector? It describes a vector as a quantity that has both magnitude and direction. Okay. Now, we can contrast that with points in R3. Okay, so a point like A. Okay, let's say this A, and it doesn't matter the exact location of A, but A is just a point in R3. And it doesn't have a magnitude or a direction, right? It's just a point sitting in space. We can't really say, okay, A is pointing in, we can't say A is kind of pointing over here, right? Okay, there's nothing to indicate that. And at the same time, it doesn't have any kind of magnitude. If we're talking about magnitude, we're usually talking about length. Excuse me. Okay, so this point A doesn't really have a magnitude or a direction. So going by this definition, something that has magnitude and direction, this is not a vector, right? But let's draw an arrow from the origin to point A. Okay. Let's keep it in green just for fun. I'll try and draw it kind of straight. Okay. So let's draw this arrow from the origin that ends at point A. Now, this arrow, unlike the point, has both magnitude and direction, right? Magnitude meaning the length. Well, this arrow has some length, and we could figure that out, maybe using Pythagorean theorem, something like that. And it's also got a direction. It's starting at the origin and pointing in the direction of A, and if it kept on going, if we would imagine it would keep going in that direction. Okay. So this does seem to be a vector. And this is how we can think about vectors as the book describes them. We can think about them as arrows that have length and direction. Now, this one's starting at the origin, but maybe, not all, the vector doesn't have to start at the origin. If we had a vector starting here, kind of an arrow starting at this point and going to this point, okay. Let's call these points B and C. Okay, this will be a vector as well. There's the vector from B to C. Okay. Now, how could we denote these vectors? I'll go ahead and I think in my notes I already have it written down later, but we could go ahead and give some notation. If I have, a vector from the origin to some point A, I could denote that as O for origin to A. So meaning I'm going from O to A. And then this arrow over the top means it's a vector. Okay, usually when I'm writing a vector, like if V is a vector, I usually denote that by putting an arrow over V or making V a bold letter. Okay, so when you write by hand, it's kind of hard to tell what's bold and what's not, right? So usually what I'll do to denote a vector is put an arrow over the top of it. And that keeps it separate in our minds from just some variable x. Okay. If we have a arrow over top, that means it's a vector. Okay. So if I wanted to denote the vector from the origin to A, I could write that like this. If I wanted to denote the vector from B to C, okay, well, I'm going from B to C, and I put the arrow over top to denote vector. Okay. Now, as I just said, we can think of the arrow from the origin to the point A as a vector. Okay, it's got magnitude and direction. And I've also already said that we usually denote vectors by bold letters or letters with arrows over them. So that's what I just said. And as we've already pointed out, vectors don't have to start at the origin. So this vector from A to B, that's a vector as well, right? Going from A to B. Now I could just say, okay, that I'm going to just call that vector V, or I could have also called it AB with an arrow over it. So in this case, the vector V is equal to the vector AB. Okay. Now the textbook has a lot of terminology. For example, this type of vector, I believe they refer to as a position vector, meaning, okay, we have a point here that's kind of like a position. Okay, so this vector, starting at the origin and ending at that position, would be a position vector. Okay. Don't get too hung up on the terminology. When the terminology is important, I'll kind of emphasize it. So I haven't seen any terminology that's super important so far besides the term vector. Okay. Now, a vector, I'll kind of explain what I mean here. I'll give you the statement first. A vector is independent of its initial point and endpoint. Okay, so let's look at these two vectors. Okay. Now, these vectors have the same length, and they're pointing they're parallel. They're completely parallel. They're pointing in the same direction, right? So if I kind of highlighted this vector, and let's say I drag it. This iPad's good because it kind of lets me drag things. Let's compare these two vectors. Okay, so I want to drag the whole thing. Okay, so if I drag this vector, okay, over here, I see they completely line up, right? These are they're pointing in the same direction. They have the same length. Okay, so okay, but the only difference is these things have different, start points and end points. But those start points and end points don't matter. The vector is completely determined by its magnitude and direction. Okay, so these two vectors, V and W, have the same magnitude and same direction, right? Okay, so they're completely equivalent. We could say they're equivalent vectors, or we could say they're equal. So the vector V is equal to the vector W. Okay, so again, starting point, ending point don't really matter. Okay. Now, a vector is also independent of the way we represent it. All right. So so far what we've done is we've just drawn a bunch of stuff, right? And you're probably asking yourselves, okay, where are the numbers? How do we write this down numerically? And the answer is there's a lot of ways to do that. Okay. We could use something in the Cartesian coordinates, the rectangular coordinates, like we're used to. We could write these vectors in terms of X, Y, and Z. We could also write these vectors in terms of like polar coordinates or spherical coordinates, something like that, and that would be just as valid. And so there's a couple different ways to write these vectors, but really the vector it doesn't matter how you write it, okay, what method you use to write it. The vector is kind of independent of all that, right? Like this picture here, okay, this is the vector, and it doesn't matter how, what kind of jargon we use to describe it. It's all describing the same vector. This is, I would say this point is very important, and then this point, okay, that's important as well, but maybe you won't encounter that as much. So as I said, there's a couple of different ways to write these vectors. We will introduce a kind of standard way, and actually maybe a couple ways to write these vectors. Okay, so we will get to the numerical representations in a minute. Now, once we have vectors, before we talk about representing vectors, before we talk about how to represent these vectors, let's talk about what we can do with these vectors. Okay, if I'm given, and let's think about, before we think about vectors, let's just talk about numbers real quick. Okay, so if I'm given two numbers in R, remember R is the set of our real numbers, right? All our possible numbers that we're used to. Positive, negative decimals, fractions, irrationals, whatever. If we're given two numbers in the two real numbers, what can we do with those? Well, we could add them together in this process, in this operation called addition, and we could multiply them together, right? Okay, so that's for numbers. Are there similar operations for vectors? And, we would like to develop some similar operations. Let's start with addition. Addition is going to be the more clear cut of the two. Okay. So let's talk about addition of vectors. So let's work with these vectors v and w, again in the x, y, z plane, the three-dimensional plane. A quick disclaimer, okay? I'm doing everything in R3 because I'm trying to get you guys used to R3, right? But we could also do this in R2, right? Okay. If I drew the xy plane, okay. This thing's a vector, right? In the same way we've seen vectors in R3. Okay, so vectors are not something that are unique to R3. Really, they work in any dimension. Okay, so R2, R3, R4, and so on. We have, vectors. And we even have vectors in just R, the real numbers, okay? It's just that in R, a vector is the same thing as a number. But I don't want you guys to get freaked out like, okay, well, because you'll be asked questions about vectors in R2, R3, and so on. So all these concepts we're going over work pretty much regardless of the dimension. Okay, so it could be 2 dimensions, 3 dimensions, so on. Okay. So let's get back to our operations. I have these vectors v and w, and I want to figure out a way to add them together. What does it mean to add them together? Okay. So let's say I would like to add the vectors v and w together. Okay, so let's find v, actually I'll write this over here. What's v plus w? Again, I'm putting arrows over these letters to denote vectors. Well, when we're thinking about things graphically, what we can do is to add to add w to v. What I'm gonna do is let's kind of bring this over here for a second. Okay, so I'm trying to add w to v. How can I do that? Basically, what I'm going to do is I'm going to take w and just tack it on to v. Okay, so how do I do that? What I'm going to do is I'm basically going to just slide the vector w until the tail of this vector is at the tip of this vector. And we can call this, tip to tail, meaning, okay, the tip of V should be on the tail of W. Okay, so when I do that, when I drag W over here, okay, what is that going to look like? What's it going to give me? Okay, I would end up with this thing, right? And let's make this kind of a dotted line just to kind of keep it separate from W. Okay. So I've dragged a copy of W over here, okay? And I've put the tip of V up to the tail of W, or my copy of W. Okay. Now, this, if I draw uh, an arrow from my origin to the tip of this combination here, that's going to give me a new vector. Let's put that in yellow. Okay, so I get this third vector here. And this vector is going to be V plus W. Okay, so that's how we could add two vectors. And you see how this forms a nice triangle, right? We have V being one side of our triangle. We have this kind of copy of W being the other side. And then this thing in this long side here, this V plus W, this hypotenuse, or this third side of the triangle, that's going to be the sum of my two vectors. Okay, and since when I add two vectors, okay, I can always make this kind of triangle. We can call this the triangle law. Now, there's also a version called the parallelogram law. Okay, this is the axis, right? So this axis is kind of getting in the way. So let's kind of, I guess we could make it a dotted line as well. Okay, so that's our axis. Now, we could have also done something called the parallelogram law, okay? So if let's kind of start from scratch. Okay, so I'm starting with my vectors V and W, and I want to figure out what V plus W is, okay? So again, I could drag W. Okay. So I could drag W here, okay? And I could also do it the other way. I could kind of drag V so I could drag V here, okay? Now, notice this forms a parallelogram, right? And excuse me, the line down the middle of this parallelogram is going to be my V plus W. So I end up at the same place. Okay, so both ways work. Okay. If really the parallelogram law is not going to be too important for us, really just use this. If you're doing things graphically, just use this tip to tail method to do vector addition. And I've kind of given the game away. Okay, we've added these two vectors together. Okay, we've developed this process of adding two vectors. We call this addition of vectors, creatively enough, vector addition. Okay, so that's what we've just done here. We've done vector addition. Now, just like with normal addition, we have V plus W equals W plus V. We have this commutative law of addition, okay? And we'll talk about this later on, but it's an important property. It works just like normal addition, essentially. Okay. Now, here might be a good time to introduce something called the zero vector, okay? Which again, we denote vectors as boldface or characters with arrows over them. So the zero vector is usually written as like a bold zero or a zero with the vector, the little arrow over it. Okay. And this is what I'll be using. Okay. Now, what is the zero vector? It's a vector with length 0. Okay. So let's say I have, Really? Okay. Like for instance, if I was going to draw a vector starting at the origin with length 0, well, it wouldn't go anywhere, right? I would start at the origin and then it would just stay at the origin because it has length 0. So if I was going to draw the 0 vector starting at the origin, it would just be that yellow point there. It would just be the origin itself. And this is the only vector that doesn't have a real direction. Okay. It's a little bit of a quibble, you know. So it's 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 unique in that this is the only vector that doesn't have like a clear direction. Okay. Now, an interesting thing about the 0 vector. Okay, let's, you know, I had a vector here before. Okay, if I have this green vector w, what is the 0 vector plus w? Okay, well, if I do my tip to tail method, okay, I would put the tail of the 0 vector at the tip of w. Okay, so I'll put a copy of the 0 vector there. Okay, and then where do I end up? Well, I don't go anywhere, right? I'm still just at the tip of w. Okay, so really the 0 vector plus the w vector is just the w vector. So again, it works exactly like addition. You know, when I'm adding numbers, when I'm adding 0 to a number, it doesn't go anywhere, right? I just end up with the same number. Same thing with vectors. If I add the 0 vector to some vector, I just end up with that same vector. Okay. So again, we've done everything graphically. So you might be asking, okay, where are the numbers? All right, we're getting there, but I'm going to introduce them a bit later. I'm kind of following the textbook here. We are going to see how to do this numerically once we introduce components. But before we do that, let's stay kind of in this graphical mode, and let's talk about multiplication. How can we multiply vectors? Is there a way to multiply two vectors together? And it turns out that yes, there are, and actually there's a couple ways to do that. But that's even a bit complicated. We're going to do some version of that in 12.3 in the very next section, but let's set that aside for now and let's do something even more simple. Okay. Instead of multiplying two vectors together, let's see what happens, and let's try and develop a way to develop a vector by a number. Okay. So let's say I have this vector v, okay, and let's multiply it by just a number, okay? I'm multiplying this vector, okay, so this is a vector, right? And I want to multiply it by the number 2, okay? Now, it's just a really intuitive way to think about it. What do you think would happen here? Okay, take a second and think about it. Pause the video if you like. What's going to happen is the vector v is just going to double in length. It's going to keep the same direction, and everything else is just going to double. Okay, so if I was going to go from v to 2v, it would just look like this. Okay, so this is my 2v. Okay, so pretty clear. What about 0.5v? Okay, well, if I was going to do 0.5v, okay, I would start with v and multiply by 0.5. Okay, so that would cut my vector in half, right? The direction would stay the same, but I would only be half as long. All right, so I'd end up with that vector. Now, what about negative 1v? Okay, so let's kind of undo this. All right, so that's my v. What if I had negative 1v? Okay, well, instead of extending in this direction, all right, negative 1v would kind of be coming out the backside. So this v is pointing, this vector v is pointing in some direction. if instead I had moved in the completely opposite direction, kind of this way, all right, and moved that same distance of v, this would be negative 1v. Okay, so pretty clear. Now, what's going on here? These real numbers, what kind of effect are they having on these vectors? Really, it's a matter of scaling, right? We're stretching these vectors, kind of stretching them uh, along their lines or maybe in the opposite directions. But really, um, we could think about our vector v as fixed. And if I'm multiplying by a number larger than 1, it's like I'm stretching this vector out this way. I'm scaling it up, right? Okay, and then if I'm multiplying by a fraction, it's like I'm scaling it down. I'm kind of crunching it in, okay? If I multiply by a negative number, it's like I've scrunched v up so much that it started to come out the back way, come out this way, okay? So it's all about scaling. Okay. So as I said, we have this scaling effect when we're multiplying by a real number. And so we're scaling by this factor here. These real numbers are the factor I'm scaling by. So we're going to call these numbers scalars, okay? So that's how we differentiate between a vector and a number, okay? You know, we have our vectors, and then we call our numbers that we multiply by, we call those scalars. So if I like have a times v, where a is a number, okay, we're gonna, instead of just calling that a number, we're gonna call it our scalar. Okay. Now, when I multiply a vector by a scalar, okay, there's a special name for that. It's called scalar multiplication. So now we have two operations with vectors. We have vector additions where we can add one vector to another, and we have scalar multiplication, and we can combine those. So let's, we have our vectors v and w here. Let's try and find v minus 2w. Okay, and again, we're just doing this graphically. Okay, so first of all, let's find negative 2w, right? Because v minus 2w, what is that? Well, that's the same as v plus negative 2w. Okay, so I know how to add one vector to another. Okay, so if I can figure out what this vector looks like, I can easily add it to v. Okay, so let's first figure out what the vector negative 2w looks like. Well, as I said, that's kind of like I have this I kind of scrunch v up and take it out the backside, and it's actually a factor of 2. So let's say that's negative 2w. Okay, boom. Okay. Now I want to add that to my vector v. So what am I going to do? I'm going to drag, see if I can do it. I'm going to drag that and put it at the tip of v. Okay. And then I draw a line from my origin, or really it's not necessarily the origin, but it's the base of my vector v, okay, which just happens to be at the origin. So I draw a line from here to the tip of this, okay, and then this yellow line would be the vector v minus 2w. Okay, so I've done my little equation here. Okay, so again, we've seen how to do this graphically. Okay. Now let's start figuring out how, we've done everything graphically. Let's start getting into some numbers, so we don't have to draw this stuff every time we want to add two vectors. So let's a vector has direction and magnitude. So let's think about direction first. How can we denote a vector that let's say we're working in rectangular coordinates, Cartesian coordinates. How could we denote a vector that moves, let's say, 5 units in the x direction, positive x direction, positive 2 units in the y direction, and negative 3 units in the z direction? How could we write something like that? Well, let's just put these kind of pointy parentheses, okay? And then let's put our kind of our movements in each of these spots, okay? So this first arrow here, this 5, okay, that's going to be the x component of my vector, meaning, okay, I'm moving 5 units in the x direction here. Then this 2 is going to be the y component of my vector. So I'm moving 2 units, positive 2 in the y direction. And then finally, I have my z component, meaning here I'm moving negative 3 units in the z direction. Okay. So again, these entries are the components of my vector. All right, so what would that look like? Where could we draw this vector? So this is a vector that moves, let's say, 5 units in the x direction, 2 units in the y direction, negative 3 units in the z direction. So if we were going to draw it with its base at the origin, okay, let's see, where would this vector go? Let's see, it's moving 1, 2, 3, 4, 5 units in the x direction, right? Positive, right? This is the positive axis, negative, positive, negative, positive, negative. Okay. So we've moved 5 units in the x direction. Okay. Now we want to move 2 units in the y direction. Okay. So our y direction is going this way, 1, 2. So now, okay, we've moved 1, 2 essentially. And then we need to move negative 3 units in the z direction. So I need to move down 3. Okay, so 1, 2, 3. Okay. So I've gone here. Okay, so I've kind of got this triangle, and then I move 3 units down. Okay, so maybe I end up, this is where my point is, if you can visualize that three-dimensional plane. Okay, now if I was going to draw my vector with its base at the origin and its point at that point, or its tip at that point, that vector would look like this. Okay, so maybe that's my vector. Now, we could find its magnitude, right? Pythagorean theorem, we'll go over that in a bit. But what I want to drive home is that, okay, this is just one of the places we could have drawn that vector. Remember, the starting point of our vector doesn't really matter, okay? So if that vector, if I had started my vector over here at this point, okay, whatever this point is, and then moved in those same directions, I would have ended up here. And this is the same vector. Remember, these vectors are equivalent. If I call this V and this W, then I have V is equal to W because they have the same length and they're moving in the same direction. Okay. So remember that property. Okay. Now, we've seen, if we're kind of given directions, we can draw a vector, right? On the other hand, let's consider a vector V, okay, with its base at the origin and its tip at some point, okay? So now what we have here we have a vector that ends at this point. Okay, so this, remember, this is not a this is not notation for a vector here. I have parentheses, not those kind of sharp parentheses. I have the rounded parentheses here. Okay, the difference is, okay, this is a vector. Okay, this is a point. Okay, so this thing is just a point. So these parentheses, these numbers in parentheses denote this ending point here. And then what's going on with this vector? Well, this vector and these points have a lot in common. Okay, if my vector starts at the origin, okay, and goes until that endpoint, okay, how many units is it going to move in the x direction? Well, it's going to move 3 units in the x direction, and then it's going to move, 4 units in the y direction, and then it's going to move -2 units. I messed up my scaling, but it ends up at the same place. Okay. So what I'm saying is, if we have a vector that starts at the origin and ends at some point, we could write, okay, let's say I have a vector that starts at the origin and ends at some point, x, y, z. How can I write the vector that ends at this point? Well, I just changed the rounded parentheses to sharp parentheses, okay? And this denotes my vector now, okay? So now let's drive home the difference, okay? Just to be a little redundant. Let's look at this here. This rounded parentheses here denotes this point, just that white point. On the other hand, these sharp parentheses denote this vector v, okay? So you can think of, okay, rounded parentheses as the point, the sharp parentheses is the arrow that ends at that point. Okay. What about vectors that don't have their base at the origin? How can we write those? So let's say I have a vector that starts at this point. Okay, we have rounded parentheses, so that's talking about just that point there, rounded parentheses, that point there. So how can I write this vector? How can I write, how can I denote this vector? It's still all about movement in x, y, and z direction. So this vector is starting, it's got an initial point here and a terminal point here, okay? As we move from initial to terminal, how many x units are we moving? Well, we're going from 4 to 0, right? So that means I move -4 in the x direction, okay? In other words, x2 minus x1. Now, how many units do I move in the y direction? Well, I'm going from -1 to -2, so I'm moving, let's see, -1 in the y direction. In other words, y2 minus y1. And then I'm going from 0 to 3, so I'm adding 3 in the z direction. In other words, z2 minus z1. Okay, and that's what I'm writing here. Going back to the 0 vector for a minute. So this is all about just writing components of a vector. We're looking at a vector and we're trying to write out this vector numerically, right? So how can we write out the 0 vector? Well, the 0 vector is just the vector, the sharp parentheses with all zeros in there. Okay. So again, these components of a vector can be thought of as the direction the vector is moving, right? We move 3 units in the x direction, 2 units in the y direction, 1 unit in the z direction. Okay, and if we kind of think about those as a whole, that gives us like one total direction, right? Now, remember, a vector is a direction and a magnitude. Magnitude, being kind of synonymous with length here. Okay, so we've talked about direction. What are the lengths of these vectors? How do we find those? So let's assume we have a vector v where it's got components a, b, and c. So it moves a units in the x direction, b units in the y direction, c units in the z direction. Okay, what's the length of that vector? Okay, what's the total distance it moves from, let's say, initial point to terminal point? Okay. Well, it's just Pythagorean theorem. Okay, essentially, this might look a little strange to you because we have 3 components here: a squared plus b squared plus c squared. Okay, this is going to give us the length of our vector if we take the square root. Now, this absolute value of a vector, okay, we're used to taking absolute values of numbers, right? Like -3, absolute value of -3 is 3. Okay. Now I have, it looks like I'm doing the absolute value of a vector. What does that mean? Well, this is not absolute value. Okay, this is not changing. This is not about changing negative signs to positive signs. This is just notation. Okay. If I see a vector with absolute value bars or bars around it, this just means the length of vector v. Okay, so maybe it's a little confusing, and that's why I prefer this notation where it's double bars. Okay, because now it's clear that this is not an absolute value bar, or this is not absolute value, right? Okay, so these are the same thing. Okay, so again, this is just the same thing, the length of vector v. I put both of these down because I might, this is the way mathematicians would write it. So this is the way I will tend to write it unconsciously. So if you see that, these are the same thing. Okay, so back to our discussion about magnitude. Let me see if I can find it. I had a visualization of why this works. Maybe I'll just draw it real quick. Okay, so let's draw our 3D plane real quick. And let's say I want to find, let's say I have a vector, let's do it in blue. So I have this vector here. I want to find the length of that, okay? And this vector has, let's call it vector v. Okay, let's call it vector v. And this v, it has x, y, and z components. Okay. Now, why is it that the length of that vector is x squared plus y squared plus z squared? Why is it the square root of the sum of the squares of the components? It's basically just Pythagorean theorem used a couple times. So let's say, okay, this vector, it's got kind of alignment like this. If I drew it down to the plane, it would go like that, and then kind of comes out here, and I got this 90-degree angle. Okay. So clearly, if I know, let's say this is side A and this is side, it's got length A, like length B on these sides. So if I can figure out what A and B are, then I can find this side by Pythagorean theorem, right? Just normal Pythagorean theorem. Okay, well, what is B, first of all? Well, B is just the Z component, right? B is just the distance from this plane here, where Z is equal to 0, up until we get to that tip of my vector, okay? So this is just distance z, okay? Now, what is this distance a? Okay, well, let's think about this plane lying flat here, okay? This distance is the x-coordinate, or excuse me, no, this is my y-axis, x-axis, z-axis. So this distance is my y-coordinate, this distance is my x-coordinate. So this distance a is equal to square root of x squared plus y squared. Okay. So this thing has this value. Okay. So now I know these two values. I know this value is z, and I know this value is this thing here. Okay. So the length of my original vector, my blue vector. Okay. So the length of v would be what? What's my formula? Square root of Pythagorean theorem. Okay. X squared plus y squared squared plus z squared. Okay. And then I simplify that. And it simplifies to this. Okay, so it works out really nicely. Okay. So the short story is if I have a vector with components, okay, a, b, and c, the length of that vector is just going to be, well, I've already written it. It's here. And this works in 3 dimensions. We know it works in 2 dimensions. If it's 2 dimensions, if I'm talking about a 2-dimensional vector, well, that's just the Pythagorean theorem, right? If my vector is in 2 dimensions, it's just a, b. Well, then by Pythagorean theorem, I know it's a squared, square root of a squared plus b squared. And this works for any dimensions. If I do 5 dimensions, if my vector is a, b, c, d, e, what's the length of that? Well, now it's just a squared plus b squared plus c squared plus d squared plus e squared. Okay, so it works no matter what dimension. Okay, but in this course, I'm trying to point stuff out to you from higher dimensions, but we're pretty much always going to be in 3 dimensions. So a quick example, okay, let's say v is equal to this vector 4, 0, 3, -3. What's the length of that? What's the length, the magnitude of that vector? You can work it out and look at these steps and see that the magnitude is 5. Okay, so the total length of that vector is 5. Okay, so now we have a way to represent vectors by components. That kind of tells the direction, and we can find their magnitudes from those components as well. And let's now see how we deal with our operations vector addition and scalar multiplication. Okay, so let's say I have 2 vectors v and w. Okay, with these components. What's my vector addition? How do I do my vector addition? Well, it's really straightforward. I just add my components together. Okay. So let's see an example real quick. Let's say I have the vectors 2, 0, 7, and -1, 3, 9. Okay. Let's call this v, this w. Okay, what's v plus w? I'm just going to add the components together. I add 2 to -1. I add 0 to 3. I add 7 to 9. And then I just simplify. And I get this. So really simple. Okay, so that's vector addition. What about scalar multiplication? Again, really simple. Okay, if S is my scalar, remember scalar is just a number, right? And I multiply my vector V by my scalar. I just multiply all my components by that scalar, okay? So again, an example. Let's say I have a vector V is equal to 3, 1, 6. Okay. What is 2 times V? Well, I just multiply all my components by 2. simplify. Okay, and then we could do the same kind of algebra, and I think it's clear what this would be. I'm not going to work through this. Pause it and work through it on your own. How about that? Now let's see some properties of vectors, and these are important. Okay, so we already talked about one so far. This is kind of this commutative law of addition. A plus B is equal to B plus A. Okay, and then we have this would be the associative law of addition. Okay, and then this would be what we would call identity of addition, inverse of addition, and so on. Okay, so don't get too hung up on the names I'm spitting out. I'm just showing off. Look at these properties, and there's a couple more, and you'll see that they're pretty straightforward. They're what we're used to from regular arithmetic, but it's not a foregone conclusion that these carry over to vectors. Okay, so and if you don't see it here, don't assume it's true. Okay, so not everything from normal arithmetic is going to carry over to vectors, but these properties definitely do, 1 through 8. And I would say it's a very useful exercise to try and prove these for yourself. Okay, or you don't have to call it a proof if that intimidates you. Call it check these for yourselves. So how could you do that? Okay, let A equal x1 y1 z1. Let the vector B equal x2, y2, z2, and C and D just be some real numbers, okay? Now, write out, component by component, the left and right side of each of these, okay? As an example, if I wanted to check that A plus B does in fact equal B plus A, I would write out the left side by components, okay? What's the left side? Well, I'm gonna rewrite A by components, x1, y1, z1. I'm going to rewrite V by components, okay? And then I'm going to do my operation of vector addition. Well, I know by vector addition, I just add them up, add these components up, okay? Okay, and by my regular commutative law of addition, I know that x1 plus x2, remember, x1 plus x2 are just numbers, right? Inside this component. I know that x1 plus x2 is equal to x2 plus x1. And same thing for y1 plus y2. That's equal to y2 plus y1. Okay. So inside these components, I can just switch the order, and then I can pull these back apart. And then that's equal to b plus a. Okay. So maybe it's a little weird. Maybe that seems kind of, maybe it seems really obvious and stupid and not worth doing from your point of view. This is kind of stuff you would do if you were doing proofs and things like that in higher level math classes. So it is kind of stupid, but try and do some similar steps with these and see what you come up with, and it should really just help enforce that these rules hold and make you a bit more comfortable with them. Getting close to the end now. Okay, basis vectors. Okay, so this is another way to represent vectors. Okay, so consider these vectors, and I've tried to kind of write I, J, and K in bold type because that's how the textbook does it. They use bold for I, J, and K as opposed to like the letters with the arrows over them. Okay. So let's call I the vector 1, 0, 0. So meaning it moves 1 unit in the x direction. J is the vector that moves 1 unit in the y direction. And K is the vector that moves 1 unit in the z direction. Okay. So if I was going to graph these, I could graph them like this. I got I, J, and K, and they kind of move along the axes. Now it might be clear, but if I draw any vector, what color haven't we used here? Let's use red. Okay. If I drew this vector here, I could make this red vector using a combination of blue, yellow, and green, meaning my basis vectors I, J, and K. Okay, and that's a very important quality. This idea of a basis, we call I, J, and K a basis for R3. Meaning if I pick any vector in R3, I can make that vector out of a combination of I, j, and k. So as an example, let's say we have the vector v, and v is equal to what you see here. V is equal to 7, negative 0.6, and 137. Okay, I can write that as a combination of my basis vectors. It would be 7i minus 0.6j plus 137k. Okay, and you will see this notation a lot in the textbook. Okay, the textbook will use this ijk notation, and so we will use it in our lectures. Okay, and if that seems weird to you, just write out what I is. Okay, what is I? I is the vector 1, 0, 0. Okay, and I know from my scalar multiplication that 7 times that vector would give me this vector, right? Okay. And then what's negative 6 times j? Well, j j is what vector? This, right? And then I have this. Okay, and now add all these up, and you should end up with our original vector v. Now, that's all I have for I, j, and k at this point. Don't lose track of I, j, and k, what these are. Okay, we are going to use these a lot in the future. Okay. A quick word about unit vectors. Again, this is maybe something that's introduced in this section, but we're going to deal with a lot more in sections to come. What is a unit vector? Okay. Unit meaning one. A unit vector is just any vector whose magnitude / length is 1. Okay, so an example, okay, that vector I, okay, that's a unit vector. And actually all those basis vectors I, j, and k, those are all unit vectors. They all have length 1, right? Okay, because I just have that number 1 in the first component and the rest are zeros, so my length is 1. Now, a unit vector can point in any direction. So let's say v is this vector here, okay? So it's kind of pointing, if I do a quick drawing of the 3D plane, where's v pointing? Well, it's moving in the x direction, y direction, z direction, all kind of equally. So it's kind of hard to draw. It's kind of coming out of the screen. Okay, it's kind of going like that, right? So it's not one of those I, j, or k direct vectors. It's not along any of the axes, but it's still a unit vector, and you can check this. You know, what's the length of that vector v? It'll be 1 over square root of 3 squared plus 1 over square root of 3 squared plus 1 over square root of 3 squared, which is equal to 1 over 3 plus 1 over 3 plus 1 over 3. In other words, square root of 1. So 1. It's got length 1. So it's a unit vector. Now, if we're given some vector v that's not a unit vector, we might want to find a vector pointing in the same direction that is a unit vector. Okay. So for example, let's say v, now let's say v is this vector here, negative 3, 0, 4. And let's say that's this blue vector. So it kind of goes negative 1, 2, 3, and then it goes up 4, 1, 2, 3, 4. Okay, goes to this point here. Okay. Now, can we, you know, this is obvious. This maybe you can tell already. This is more than 1 unit long, right? What if we wanted to find a unit vector in that direction? It would be somewhere along this blue line. But what would be the coordinates of that endpoint here? You know, how could we write this vector? Well, let's find out. How could we do that? Okay. Basically, what we're going to do is we're going to first figure out what the exact magnitude of this vector is, and then we're going to divide each of the components by that magnitude. Okay. So, and this only works if v is not the 0 vector, right? If v was if v is the 0 vector, that's just that vector there, right? There's no way we can make this into a unit vector. Okay, so we're trying to find a unit vector in the direction of that blue vector. So the first thing I do is I find, okay, what's the magnitude of v? Well, that's going to be 5. Okay. Now, if I divide v by 5, in other words, I do this, what do I end up with? Okay, let's just take the magnitude real quick, and this is kind of a trick. Okay, what would the magnitude of this be? Okay, it would be 1 over, let's see, it'd be, you know, I know some techniques to make this a lot quicker. Okay, first of all, what is 1 over 5 v? That would be negative 3 over 5, 0, 4 over 5, right? Okay. Now let's find the magnitude of this thing. Well, that's going to be square root negative 3 over 5 squared plus 4 over 5 squared equals square root of 25 over 25. You can check that, equals 1. All right, so we found that the magnitude of this vector here is 1, so it's a unit vector. Okay. Now that might have seemed complicated, but if we have a vector v, if we want to make it into a unit vector, we just have to divide by its magnitude. So for any vector v, 1 over magnitude of v times v, vector v, is going to be a unit vector in the direction of v. Okay, so that kind of covers the background for vectors. Now we can finally talk about applications. Okay, this is the quick last section. The main applications for this section are force. Okay, basically, I am going to represent a physical force by a vector. Okay, so this is very physics oriented. Okay. So, what is a force? You know, I'm kind of stretching myself here. Force is what? Magnitude, or not magnitude, mass times acceleration, right? F equals ma. That's like the one thing I remember from physics. Okay. Well, m is just a number, it's a mass, right? And then a, okay, I could be accelerating in a couple different directions. So, you know, this is kind of a is kind of a direction. So this is like a vector. Okay. I have a magnitude and I have a direction. Okay. Okay. Now, first, before we get into some, you know, more complicated applications, what's you know, one way we might see this? You might see this, and this is kind of this is usually kind of divorced from x, y, and z coordinates. Okay, this is usually written like this. Let's say I have just the xy plane, two-dimensional. Let's do things two-dimensional for now, just to keep it simple. Let's say I'm told, okay, I have a force of 200 newtons, and it's applied to an object at an angle of 30 degrees above the horizontal. Okay, so like I have an angle 30 degrees, and I'm told I'm applying a force of 200 newtons in that direction. So I'm not really talking about x, y, and z of vectors here. It's like my magnitude, it doesn't depend on these x and y coordinates of this plane. And in fact, you know, there might not even be a plane. Maybe it's better just to think of this as like the ground, or kind of drawing a little picture of our physical situation. I'm applying a force of 200 newtons at an angle of 30 degrees above the horizontal. So the magnitude of this vector is just the amount of force I'm applying, okay, 200. And then the direction would be, okay, 30 degrees above the horizontal. Okay. So that's the first thing we might see. All right. Now, the application, like the tools from our mathematical vectors that can be used here are, you know, we have a couple good examples. Let's look at number 33 from the textbook, okay? And if you don't have to look it up, I'll tell you what it says. It gives us a drawing. Okay, so it gives us this. It's a force of 200 newtons, and it's applied in the direction that's 60 degrees above the horizontal. And then we have a force of 300 newtons, and that's applied just directly along the horizontal, okay? And we're adding these forces together, so we're finding the resultant force, okay? So think about it like this. Maybe there's like a particle here, okay? And it's hit by two different objects at the same time. And maybe one object it hits with a force of 200 newtons going this way, and a force of 300 newtons going, the other object hits with a force of 300 newtons going this way, okay? What's gonna happen to this particle? It's gonna go ricocheting off, but in what direction and with what force, okay? So what we need to do is find the resultant force, okay? And this is just a matter of vector addition, okay? But first, we kind of need, maybe I should have done number 30 first, and that'd be logical. First, okay, I know, basically I do want to kind of break this down into horizontal and vertical pieces, okay? This vector, this 300 newtons, right? That's just completely horizontal. I don't need to break that down into anything. But this vector here, I want to break this down into a horizontal force and a vertical force. So this is, you know, we could call this decomposition of force. So I want to break this one force down into its two components, its horizontal component and its vertical component. Okay. And it's just a little bit of trig. Okay, so I know this angle is 60 degrees. I know this force moving in this direction is 200 newtons. Okay, so what's the horizontal component? Okay, okay. Think about this as a hypotenuse. Okay, what would be the length of this side? Okay, it would be the hypotenuse times cosine of 60, right? And what would the length of this side be? It'd be hypotenuse times sine of 60. So the horizontal force would be 200 times cosine of 60. And the vertical force would be 200 times sine of 60. Okay. Well, what's sine of 60? That's what, square root of 3 over 2. And then cosine of 60 is 1/2. Okay. So basically what I have is horizontal component of that, vertical component of this. So this force here, I could write as a vector. Let's see, 100 times square root of 3. Okay. And now if I was going to write this force as a vector, what would that be? Well, it would just be 300, 0. Now, what's the net force? I'm just going to add these two together. Okay. So the resultant force, we could call it F, vector F. would be, and actually instead of 300, this would be negative 300, right? Because it's moving in the opposite direction. Okay, we got to be careful there. We got to be careful of sign. So the resultant force would be negative 300 plus 100, so negative 200. And then 0 plus 100 times square root of 3. So 100 times square root of 3. Okay. So my resultant force would move, it would be negative 200 units in the horizontal direction, and it would be going off like this. So basically, the resultant force is kind of going off this way. Now, the question also asks us, okay, it wants us to find the magnitude of the force. Okay, so we have the components. What's the magnitude of that vector? It's just Pythagorean theorem, right? Okay, so this is my magnitude. You can double check that. Square root of 7 times 100. So this force has a magnitude of square root of 7 times 100. Now the question is, what's the angle here? Okay, and they want us to measure the angle from here to here. Okay. Well, again, think about this as a hypotenuse. I have a hypotenuse that's square root of 7 times 100. And I know this side is what? It's my y components. So square root of 3 times 100. And this is negative 200. Okay. So I could just do, and I won't do it in my calculator. I'll let you guys do it. What's the angle here? What would, let's see, sine of this angle, sine of that theta, we'll call it, would be 100 times square root of 3 over 100 square root of 7. Okay, so square root of 3 over 7. Now I want to find the angle, so I take the sine inverse of both sides. So theta would be equal to sine inverse of that. Okay, that would give me this angle here. And then I do 180 minus that angle, and that should give me this angle. Call it theta 2. Okay, and really, I think we kind of covered both these problems because we kind of did a decomposition of force here. Okay, so that's it for applications, and this would be a good example of what we might cover in the Tuesday class meetings. More problems like this. We have all the mathematical knowledge we need now. It's just a matter of seeing the tricks and applying these. Okay, so that's all the material for today. Enjoy.